Come back, Chapter 8, Section 8.3. Estimating P in the binomial distribution. Compute the maximal length of error for proportions using a given level of confidence. Compute confidence intervals for P and interpret the results. Interpret poll results. Compute the sample size to be used for estimating a proportion P when we have an estimate for P. Compute the sample size to be used for estimating a proportion P when we have no estimate for P. All right, let's learn a few things about these focus points, one topic at a time. The binomial distribution is completely determined by the number of trials n and the probability p of success on a single trial. Okay, in a binomial distribution, all you need is n and probability p of success. For most experiments, the number of trials is chosen in advance. Then the distribution is completely determined by p. In this section, we consider the problem of estimating P under the assumption that N has already been selected. Okay, so we are employing what are called large sample methods. We will assume that the normal curve is a good approximation to the binomial distribution. So this is a big assumption, and when necessary, we will use sample estimates for the standard deviation. Empirical studies have shown that these methods are quite good provided NP is greater than 5 and NQ is greater than 5, where Q is 1 minus P. This is probability of failure in a single trial. All right. So you want to make sure that first make sure that NP is greater than 5 and NQ is greater than 5 before going on to these methods that are coming up now. Let R be the number of successes out of n trials in a binomial experiment. We will take the sample proportion of success, that is P hat. What is P hat? This is proportion of successes, R over N, as our point estimate for P. Okay. The population proportion of the successes P hat. So what is P hat? R over N. Okay, so this is our point estimate for P hat. Okay. So the point estimates for P and Q are P hat is R over N, Q hat is 1 minus P hat. Okay, so what is P hat? It is a point estimate for P. Therefore, Q hat is 1 minus P hat. N is number of trials, R is number of successes. To compute the bounds for the margin of error, we'll need some information about the distribution of R over N. There should be a P hat here of the same size N. It turns out that for large samples, the distribution of values is well approximated by a normal curve. Mean is P and standard error is square root PQ over N. Okay, so that's an over N. Since P hat, it should be here. Since P hat is R over N is approximately normal, we use features of the standard normal distribution to find the bounds for the difference P hat minus P. Recall that Z sub C is the number C such that and area equal to C under the standard normal curve falls between negative ZC and ZC. So this is the critical value for confidence level C. Okay. So in terms of probability, P hat minus P is between these two numbers. What does this equation mean? It says that the chances C that the numerical difference between P hat and P is between this and this. With C confidence level, our estimate P hat differs from P by no more than the margin of error, maximal margin of error. So, we call E the maximal margin of error. Here is an optional derivation, okay, an argument here. P hat is R over N. It is approximately normal with mu P sigma square root PQ over N. From section 6.6, we know that for sufficiently large N, the binomial distribution can be approximated by a normal distribution. Mu is NP. All right. Standard deviation sigma is square root NPQ. Okay. The binomial distribution can be approximated by a normal distribution with this mean and this standard deviation. If R is the number of successes out of n trials of a binomial experiment, then R is a binomial random variable with binomial distribution. We convert R to standard Z units. R minus mu over sigma. So R minus NP over square root NPQ. So divide this by n and divide the denominator by n. We are allowed to do that. Division here distributes. So R over n minus NP over n. The n's cancel and you have a P. Here, that's square root NPQ. This is n, when it goes inside the square root, becomes n squared, you see. And one of the n's cancel, so you have square root of PQ over n. The n is inside the radical. So, what is this? This is P hat. The P hat distribution is approximated by normal curve. So, this is standard. So, P hat distribution is approximated by a normal curve with mu. Its mean is P and its standard deviation is this. That's all we are saying. So, the probability is C that Z lies in the interval negative ZC to ZC, because an area equal to C under the standard normal curve lies between negative ZC to ZC. That is, probability negative ZC to ZC, Z between these two is C. So, Z is P hat minus P over square root PQ over N. We have just rewritten this with a P hat. Okay, so all of that is Z, is between negative ZC to ZC, and probability of that inequality is C. Multiply all the parts by the denominator to get rid of the denominator. So you see, you have these limits. These are this is basically your maximal marginal error. Okay. So to find a C confidence interval for P, we will use E in place of the expression. Okay, so E, we get, okay, E is this one, right? So you get, looks like P hat lives there, P hat lives there. All right. And P hat lives here, and P hat lives here. Okay. So equation 20 states that the probability is C, that P lies in the interval from here to here. All right. So where E is this. All right. So the interval P hat minus E to P hat plus E is the C confidence interval for P. There is one technical difficulty in computing C confidence interval. The expression E equals this requires that we know the values of P and Q. Look at that, right? But we do not know P and Q most of the situations. So instead of P, we will use P hat. Instead of Q, we will use Q hat. Q hat is 1 minus P hat. That's how we estimate E. These estimates are reliable for most practical purposes since we are dealing with large sample theory. Large sample is n times P is greater than 5 and n times Q is greater than 5. We'll summarize the information about C confidence intervals for P, the probability of success here in our next video. Until then, see you.